The first speaker I want to introduce is Karen Chan, who is a professor at the DTU University, and she is an expert in the modeling of thermodynamics and kinetics of electrified interfaces. Today, she is going to talk about pH effects in electrocatalysis. Thanks, Karen.
Okay, thank you, Clotilde, for the introduction and also for organizing this wonderful symposium. And I'm really looking forward to seeing all of the talks here. And so what I'm going to address in my talk is what I will define as pH effects in electrocatalysis. And what I mean by that are electrocatalytic activity that do not depend on a reversible hydrogen electrode scale. And that deviates from what we might expect from a simple computational hydrogen electrode model. And in particular, what I will discuss is how adsorbate dipole-field interactions, as well as solution phase reactions and mass transport, give rise to pH effects, and how pH effects in electrocatalytic activity can be signatures of these phenomena. And so before I get started, I want to acknowledge all the people who did the work. And so shown in pictures here are all of the first authors or co-first authors of the work that I will present. On this column here, we have also all the co-authors who I'm very grateful for as well as the PIs behind a lot of the efforts. And so just a very brief motivation of the vision behind all of our work. And the idea is to harness the energy from renewable sources in order to electrochemically reduce, for example, CO2 back to fuels or into industrially relevant chemicals in order to create this zero or low emission carbon cycle. These are the corresponding processes at the cathode and anode where we have CO2 reduction to various products in competition with hydrogen evolution. And from an ab initio perspective, one of the major challenges that we face is in going beyond reaction thermodynamics as given to us by a computational hydrogen electrode towards the determination of activation energies, the corresponding kinetics, and to begin to explore the impact of the electrolytes of ions and mass transport phenomena and how that affects the overall electrocatalytic activity and selectivity. So I will start with a very brief discussion of one of the major challenges that we are still tackling today, and it is the challenge to determine reaction energetics under a constant driving force. And so if we were to naively do an explicit simulation of an electrochemical reaction barrier, we are doing this at constant number of electrons, whereas in experiment, we're operating at constant potential. And this discrepancy really leads to what you can see here as a really large change in surface charge density along the reaction pathway for a typical proton-electron transfer. And we can see the effects of this in the corresponding work function for a very typical proton-electron transfer is illustrated here, where we have between 2 to 3 electron volts in a usual sized unit cell. And this is well beyond the range and potential that we would be interested in for any electrochemical process. And so how do we mitigate this not constant driving force along the reaction pathway? And in the past decade or so, there's been a variety of different methods developed, and I think we can classify them into 2 broad categories. One would be what I term extrapolation methods. And the idea is to extrapolate from our small cell calculations to an infinite cell calculation where we have a constant potential. And one possibility to do this is to do the calculation of a proton-electron transfer in a series of different size cells. And what we can see here is that when we go from a smaller to a larger cell, there is a decrease in the change in charge density. And so with enough number of calculations, one can extrapolate to the infinite cell size. And so this is kind of like a brute force approach, and it's computationally extremely expensive. And what we have developed in the past few years are capacitor models of the electrochemical interface that allows us to link the small to large cell results. But this comes with some challenges. For instance, the assumption that the reaction pathway, for instance, does not change when we change the surface charge density. And so that leads to some uncertainty in what we can determine here. And also there are some challenges associated with the need to partition the charge according to a capacitor model. And we can't always do that in general. So the alternative here are all the grand canonical methods that have proliferated in the past few years. And the general idea behind these is that we have a variable number of electrons and a countercharge in the continuum electrolytes, which can be modeled in a variety of different ways. But the main idea is this. So for instance, if we have, say, an adsorption of a CO2 molecule, for instance, this gives us a very large interfacial dipole, and in general, it changes the effective surface charge density, or the driving force for the processes we're interested in. And the idea then is to simultaneously apply charge to give excess electrons and a corresponding countercharge in a continuum electrolyte so as to offset this change and to keep the work function constant. And so there's a variety of different models that have been proposed by these authors here and beyond. And as an example here, this is a charge density isosurface that would correspond to a linearized Poisson-Boltzmann approach according to the VASP-SAW package that was determined in Richard Hennick's group. And so all of these methods would beg the question, are the methods equivalent, or when are they equivalent? And I think to answer this question, it is very useful for us to think electrostatically of the different charging components that are possible at the interface. And so shown in this cartoon here are the various charging components. For instance, explicit charge coming from a proton or hydroxide or another cation and so forth. Co-adsorbate charges, so very polar adsorbates that would lead to a dipole at the interface, which also affects the driving force for electrochemical reactions, as well as various continuum charge models, whether it's a planar countercharge or a Poisson-Boltzmann distribution and so forth. And the important thing here is to note that the various charging components in general have their own capacitance. There's no reason that they might be all equivalent in terms of capacitance. And what this actually means, and I'm taking a playbook out of Frumkin here, out of his double layer correction to kinetics, is that for a given macroscopic applied potential, the presence of all the different charging components mean that the local driving force is not a one-to-one relationship with the applied potential. One can have a variety of different interfacial potential drops as a result of having so many charging components. And what I will suggest in what follows, that this local interfacial drop that is driving the processes that we are interested in is perhaps better captured by the local surface charge density and not the overall work function as we commonly do today. And I think this idea is best illustrated with an example. And let us consider then the Volmer reaction, which is the simplest proton-electron transfer. And this is a proton-electron transfer to the surface as follows. And so let us first consider the case where we only have explicit charge. And one of the ways then to modify the driving force then is to change the concentration of charge, or to look at the reaction energetics as a function of cell size. And if we are to do so, then we obtain a relationship between the energy and the mean work function. the question is, what happens if we were to add implicit charge to the system? Like so. So for instance, in a planar countercharge, or in this particular case, I'm going with the linear Poisson-Boltzmann model. And what we find is if we were to add this contribution, what we obtain is a pretty dramatic cell size dependence. And so depending on the amount of implicit and explicit charge, we can get very different results at a given work function. So when we're mixing charging components, the work function does not uniquely determine the energetics. It depends on the proportion of implicit and explicit charge. And so in principle, if we were to do our mixed implicit-explicit simulations just out of the box, then the results are cell size dependent. And this is something that we see very, very often in all our mechanistic studies. And so what's the mitigation strategy? And it's to go to the surface charge density approach that I talked about, because if we were to then re-examine all of our energetics as a function of surface charge density, then we get just a single function. And really what this reflects is that the surface charge density is proportional to the local field, which is a good approximation of the local potential drop that is driving this process, as illustrated in this cartoon here of the Frumkin effect. And so my suggestion would be then to relate our energetics under a given charge to potential using some known charging properties of the interface, the double layer capacitance and the potential zero charge. And so this is what we have done for a number of mechanistic studies. There's some caveats here, and that is that we also need some sort of effective charge from the explicit system. With implicit simulations, we know how much we put in. And to determine that rigorously, sometimes we need to look at multiple cell sizes, which then increases the computational cost. And if we're doing our simulations under constant charge, we can have relaxation effects that won't be there under constant potential. And this is always an uncertainty that we are coping with. And in fact, what we're trying to do now is to combine this approach with some grand canonical methods so that we can get the best of both worlds. And here, for all of our investigations, we have not included any dynamics. It just becomes computationally very intractable, but I'm sure we're going to hear a lot of discussion about that this afternoon in the following talks. Okay, so this is how we cope with doing our simulations. And now what I will do is to go into some mechanistic studies of electrochemical CO2 reduction. And what I hope to be able to cover within the remaining time is two topics: dipole field interactions on a variety of catalysts, as well as briefly touch upon solution phase reactions and the impact of mass transport phenomena. Okay, and the signatures of these two are manifested as pH effects in electrocatalytic activity. Okay, so first starting with dipole field interactions. So dipole field interactions were also taking a playbook from the past, from thermal catalysis. We know from work in thermal catalysis on promoters that the absorption energies of various polar adsorbates depend on field in a pretty predictable way, dependent on the adsorbate dipole and polarizability. And what is quite special about electrochemical CO2 reduction relative to some of the other hot processes out there for sustainable energy conversion is that some of the critical intermediates are quite sensitive to the interfacial electric field. And in particular, they are particularly strong for some decisive intermediates such as CO2 and OCCO, which have these vertical polarized CO bonds. And this has a significant impact on how the pH and electrolytes affect the electrocatalytic activity. And so first off, let me start out with a cartoon of why dipole field interactions give rise to what we call pH effects. And let us consider, for instance, CO2 adsorption and CO-CMO dimerization, which are respectively the decisive steps towards the production of CO on weak binding catalysts, as well as C2 products on copper which is the only catalyst that is able to couple CO in any substantial way. And so both of these are sensitive to the field through the dipole-field interaction. And the field at the interface depends on the absolute potential. And so, for instance, it depends on the potential versus SHE, but not the RHE scale. And so in this very simple picture, this is just a line, it's not calculated, and one can, in principle, have more complex models of the interface. But in general, we'd expect a monotonic function between field and potential. And what we would see then is that negative of the potential of zero charge of the particular metal solution interface, we would have an increasing stabilization of these two intermediates through dipole field interactions. But on an RHE scale, which determines the efficiency of proton-electron transfer processes in general, a given stabilization would correspond to a very different potential and overpotential for the process. So for instance, between pH 7 and 13, a given field would correspond to an overpotential that differs by 0.36 volts. It's 60 millivolts per pH unit times 7 times 6 here is 0.36. And so we can think of dramatic pH effects that are observed experimentally for electrochemical CO2 reduction as a shift, a Nernstian shift in the RHE reference with pH. And that's perhaps contrary to some of the discussion that we see, the OH minus does not play a role in promoting these two steps. They're not involved here. So perhaps it's a bit of a misnomer to call it a pH effect because it's not directly affected by the chemical potential of the protons, the OH minus, that are produced in the reaction. And so then let us go into some examples of this effect. And I'm going to feature gold and copper because these are the very best transition metal catalysts for the production of CO and high value C2 products, respectively. So first, let us start with gold. And what I'm showing here is experimental data from our collaborators in the Tom Harmeal and Chris Hahn's group. And what is shown here is the pH dependence of hydrogen and CO production as a function of the SHE scale. And the marked difference between these two products is a significant pH dependence for hydrogen evolution and not for CO. And we'd expect that for hydrogen evolution because it's limited by proton-electron transfers. And we're changing the proton donor as we go to more and more and more acidic conditions. Whereas in the case of CO, we see no such effect, which suggests that proton-electron transfers are not involved. And instead, it suggests a field-driven chemical step being rate limiting. And this is consistent with our model results as well. And so on the basis of planar countercharge model of the energetics, we have developed a corresponding coupled kinetic transport model, accounting for buffer equilibria, diffusion, and migration, and so forth, for this mechanism of CO2 reduction to CO. And so it undergoes two proton-electron transfers, as we can see here. And this is the main results that we get in comparison to area normalized experimental activities. And so in this particular case, that the theory agrees really well with experiments, but I want to note here, and I'm going to show examples to the contrary, that in general, we can't get this quantitative on the basis of all of the issues that I have touched upon in the introduction. But in this particular case, there's some agreement, but that's not important. What is important is that what the theoretical results suggest is that we are limited by CO2 absorption under the potential range that we're normally operating in. And what this means for us then is with this dipole field hypothesis, is that the corresponding Tafel slope of the overall reaction would depend on the dipole of the CO2 as well as the double layer capacitance of this particular interface. And what this implies is that perhaps we can tune these parameters towards higher activity. I also want to note one other thing, and This is because there's a lot of importance placed on finding what one might call cardinal Tafel slopes of 60 or 120. And a lot of mechanistic analysis is based on us finding these slopes, but there's really no fundamental reason why that should be. Not in a dipole field picture and not in a proton-electron transfer picture, because we know from outer sphere electron transfer, for instance, that we're really dealing with a symmetry coefficient. And so there's no fundamental reason to be looking for these. And actually, the impact on mass transports on these also convolutes the analysis. And now I'm just going to note very briefly that we have a similar phenomenon happening on copper. And so what is shown here is experiments and the results of a kinetic model from the ab initio energetics. And you can see, like in the gold case, we have very minor scatter amongst results for C2 product production at different pHs, which again suggests that we have a field-driven chemical step. And we find theoretically that this is consistent with what we expect at higher overpotentials. Okay. So this result is more consistent with what we expect we can do in terms of accuracy. There's several orders of magnitude difference, and the standard GGA uncertainties is actually indicated by these boundaries here, and so it spans several orders of magnitude. And this is really the best one can hope for. And so what we do find in theory is that at some high overpotential region, we are indeed limited by OCCO formation, which does not have a pH dependence, but that at lower overpotentials, it could be that we have a pH dependence. And perhaps if we are able experimentally to reach this lower potential region, we would be able to see this result as well. But all in all, we do have a similar pH dependence on copper, which again suggests that it's this adsorbate field interaction that is rate limiting for the process. And this is what we should focus our catalyst discovery efforts on stabilizing. So let me return then to the question of whether or not we can design better catalysts using this mechanistic insight. And at least theoretically, I believe there is the potential for this. And let us first consider the first phenomenon, that is the adsorbate dipole effect. And our hypothesis here is that this is what is behind the promising activity that has been observed on single atom catalysts. And our hypothesis here is that the localized electronic states here give rise to more tunable adsorbate dipoles and more tunable activity for electrochemical CO2 reduction. And shown here is kind of the archetypal site motif for a single atom catalyst on nitrogen doped graphene defects. And the site motif here takes some inspiration from molecular catalysis, but in general, there's a variety of other motifs that could be stable. And so we haven't considered all of these in our analysis. And what is interesting about these materials is that what we find is that either COOH formation or CO2 formation can be rate limiting here. And this is what is illustrated in these computed free energy diagrams that include the field effect with a corresponding countercharge. And what we find on the iron catalyst, where it is suggested experimentally that it's these more coordinated site motifs that are more stable, is that in those cases, we would be limited by CO2 adsorption. Whereas for almost all of the site motifs that we have considered for nickel, it is the COOH formation step that is rate limiting. And so since this step here would involve a proton-electron transfer, we would expect a pH dependence. And this is consistent with what is seen experimentally, and this is the data taken by Peter Strasser's group. Okay, where they see no pH dependence on iron and a pH dependence for the nickel nitrogen carbon. And so we have combined all of these insights into the single atom as well as the transition metals to this overall kinetic activity volcano as a function of these two critical now descriptors, CO2 binding and COOH binding. And the color bar here corresponds to a turnover frequency. And so, as we often see in heterogeneous catalysis in general, moderate binding energies are good. And so the tip of this volcano lies where we bind both CO2 and COOH moderately. And when we bind very weakly, then the formation of these intermediates become limiting. And if we are to bind very strongly in this region, then we become poisoned with CO, as illustrated in these coverage points. So the interesting idea that is illustrated here is we have this transition metal scaling, and that the single atom catalysts tend to be shifted downwards from the transition metal scaling line, and sometimes in favor of activity. And this shift downwards along this y-axis of CO2 binding really results from the larger dipoles that are stabilized on these materials. And I illustrate this more explicitly here with the dipole for a variety of different transition metal facets, as well as both iron and nickel in a variety of different single and double vacancy sites with different nitrogen coordinations. And what we can see here is that in general, we have larger dipoles for this critical CO2 intermediate on the single atom catalyst. And we can link this to the electronic structure. In general, the single atom catalysts tend to have more narrow, more localized D states. And this gives rise to different occupancies that are associated with different dipoles. And in general, the occupancies are determined by both the position and the shape of the D band. And these single atom catalysts tend to stabilize larger dipoles as a result. And the hypothesis that results from this is perhaps there are other materials with similarly narrow localized electronic states that can be found for perhaps other processes where dipole field interactions are decisive. For instance, the CO-CO dimer. We have thus far had no alternative really to copper-based materials in electrochemical CO2 reduction, and perhaps this idea offers us some promise in developing new or more active materials there. And so now comes the question, so there were two possible descriptors of activity, so dipole moments and double layer capacitance. Can we tune the double layer capacitance? And our hypothesis here is this is actually what is responsible behind the dramatic cation effects in electrochemical CO2 reduction. And let me again try to illustrate this with a cartoon. And our hypothesis here is that cations that have smaller hydrated radii can pack in a denser way at the electrochemical interface, such that it leads to slight increases in the stabilizing interfacial electric field. And in the case of lithium versus cesium, lithium actually has a larger, looser solvation shell. And so the idea goes back to this Fromkin effects that I showed earlier when talking about the challenges in using explicit implicit models. And the idea here is that cesium, due to its smaller size, can have a slightly larger packing density and therefore a larger stabilizing field. And really, this then tunes the double layer capacitance ever so slightly in favor of higher activity. And we can account for this in a continuum way in conjunction with our constant charge simulations of the stability of the adsorbates as illustrated here. And this is something we can account for using a modification of the classic Poisson-Boltzmann model, where we add a volume exclusion term that goes to zero in the limits of small diameter of infinitesimally small ions, where then we just recover the classic Goy-Chapman theory of the interface. And we have a boundary condition in our continuum model that relates the field and charge density to the charging properties. And so these are the results of our model. And so shown here is the relative activities for C2 production on copper, as well as CO production on silver. And so everything is normalized to the activity of lithium. And in general, the theoretical and the experimental relative activities tend to be consistent. And so here we're showing relative activities because we tend to do better with relative activities, likely due to some sort of error cancellation I would not expect the absolute activities to do so well. We also compared theory and experiment in terms of the vibrational Stark shifts for CO on platinum as well as CO on copper from Binjun Su as well as Matthias Wegel's group. And in general, the trends are also in agreement, which gives some credence to our very simple hypothesis. And so on the basis of this model, the main takeaway is that small cation radii and in principle, large charges are advantageous for both C2 and CO production because they slightly increase the surface charge density and the effective double layer capacitance. So the main takeaways here would be that in electrochemical CO2 reduction, and for some other processes actually, rate limiting steps that have a strong adsorbate dipole field interaction give rise to apparent pH dependencies in activity, and that we can exploit this effect, for instance, in single atom catalysts through how they can tune the dipole, as well as cations through the field or the corresponding double layer capacitance. Okay, and so I think I'll just spend a very little time then talking about solution phase reactions. And I'm switching gears very slightly here, and I'm going to use the example of CO reduction to acetate. Okay, and so normally when we're thinking of CO reduction to C2 products, the major products that are observed are ethylene and ethanol. But what has been increasingly observed is that under alkaline conditions, we also get substantial amounts of acetate. And here, in contrast to other C2 products, it shows this very interesting pH dependence. And so on an SHE scale, we do not get pH invariant activity. It actually increases with pH, as illustrated here from Feng Zhao's data in the University of Delaware. And in addition to that, acetate shows this very interesting dependence on potential in terms of its selectivity. And it also depends on the type of copper that we are working with. And what is shown here is that there are differences in selectivity, whether we're working with copper nanoparticles, nanosheets, or oxide-derived copper. And one of the hypotheses out there for why this might be is that perhaps we have different active sites on different forms of copper, which is a very reasonable hypothesis. But when we're looking for that in the experimental data, we actually don't see this to be the case. And so shown here is data that has been painstakingly collected by two postdocs, Hendrik Heenen and Georg Kaslinger, for a number of different types of copper catalysts, both in gas diffusion as well as H-cell setups. And if we were to exclude the regions where there's a bending over that we can attribute of the activities of various C2 products due to mass transport limitations, and we look at, for instance, the region where one sees a Tafel behavior, we really don't see much of a spread. The magnitudes of the spread amongst very, very different sets of data that are normalized to area suggest to us that we have very, very similar active sites on all copper catalysts. Because in general, when you change an active site, you change the activity by orders of magnitude. And so we simply don't see that. In the case of acetates, we get slightly larger spread. But really, when we change active sites, we expect orders of magnitude shifts in the area normalized activities. And so our hypothesis here is that then we have a solution phase reaction involving OH- and its changes in the reaction environment that influences the activity towards C2s. And so we have considered that with a coupled kinetic transport model, considering this reaction mechanism, where we have considered the same rate limiting step towards C2 products on the basis of previous work, and a series of proton-electron transfers, and this critical ketene intermediate that can either undergo solution phase reaction with OH- to form acetate, or it can reabsorb and undergo proton-electron transfers towards other C2 products. And I think I'm actually nearing the end of my time. And so I think I'm going to skip over the details of this kinetic transport model and skip over to the results. And so on the basis of initio kinetics and a very simple transport model, we obtain the following selectivities as a function of potential that is, again, qualitatively consistent with experiments. And through this, we can rationalize the trends that we see. And so when it comes to the pH effect, of course, if you have a solution reaction with OH minus, then having more of that is going to increase the reaction rate towards acetate. The impact of the type of copper within this model, we rationalize it simply on the basis of the competition between kinetics and transport. And so when you have a rougher surface, you're increasing the effective rate of transport and decreasing the transport rate relative to kinetics. And vice versa, if you have a smoother surface, then the relative rate of transport is faster. And so with, say, a faster relative rate of transports, then you have less buildup of this ketene intermediate, and therefore a lower coverage of this H2CCO intermediate towards C2 products, which then would increase the corresponding activity towards this pathway. And so the selectivity is really tuned by the interplay between kinetics and transport. And we can also rationalize the potential dependence, again, on the competition between a proton-electron transfer step and the buildup of the critical intermediates towards acetate production. And so the main takeaway is that the acetate selectivity really comes from an interplay between kinetics and mass transport, and that the solution phase reaction here is the decisive factor in this interplay, and that's one can increase the selectivity to acetates by increasing the pH or by decreasing the catalyst roughness, and that we don't attribute this effect to an active site phenomenon. And so what I hope to have shown is that then the electrolyte solution reactions and mass transport can all be decisive for activity and selectivity beyond electronic structure effects that us coming from an initial perspective are so accustomed to examining, and that the corresponding pH effects can also be signatures of the mechanisms that we are investigating. And that we also have some design rules for electrochemical CO2 reductions, in that more alkaline is good, not always for the same reason, and that we can stabilize larger dipoles through looking at new materials such as single site catalysts, and that smaller cations are better for a stabilizing field. And so perhaps then I end again with the acknowledgements. So thanks for your attention here. And I hope I have just a couple minutes for questions.
Yes, Karen, thank you. Thanks a lot for the very interesting talk. And yes, you have for sure a couple of minutes for questions. And so is there any question? So if you have questions, you please can raise your hand or add your question in the chat.
Clotilda, I've lost the hand, actually. Can I just speak straight?
Sure. Hi, Alexei.
Karen, if you can a little bit explain about the calculations, how they were made, right? Because you're doing calculations of the interface of a metal and the liquid, so there are molecules, ions, reactants, the electrode itself, how, on which level everything was described. At the beginning, you said about something that is taken semi-implicitly, like through Poisson-Boltzmann things. Do you have any molecular simulations in that business here, or DFT or whatever?
Yeah, so at the beginning of my talk, I talked about explicit, implicit simulations. And so we are doing everything with, say, a static water layer. There's no dynamics, but say we have a barrier. We determine that by looking explicitly at a proton-electron transfer, and then tuning the charge of that, usually with an implicit approach. For instance, a planar countercharge or some sort of Poisson-Boltzmann kind of approximation in a continuum electrolyte.
Okay, and what is non-continuum? What is done at the molecular level, non-continuum?
So just a static water layer, like a sort of semi-hexagonal-like water layer. So there would be a proton solvated in the water layer, and then the proton.
And you just take into account the electric field, which is calculated through
the surface charge density.
Yeah, you calculate it through theoretical Poisson-Boltzmann approach, the electric field. You put it into the calculation of your molecular orientation, because when you change the voltage, orientation of the molecules will be different, right?
Yes, and so in the method that we're using, we're doing most things at constant charge, and the assumption there is that the reaction pathway does not change a lot, even when you're charging it. Because what we do is we do it at a small cell and then use that to extrapolate to a larger cell result. And so that is a source of uncertainty here, that we're assuming that we don't have this restructuring that could occur. And this is an issue, right? And that's why there are some grand canonical methods that look to charge the surface. The issue there, though, is that the capacitances, especially when you add a water layer, would then not be correct either. And so there are problems with both approaches. Either you do it at constant charge, and then you extrapolate that to a large cell and a constant potential, or you try to compensate for that by adding all of this charge at the same time. But then the problem is then you're not adding it at a very reasonable capacitance. And then in that sense, then you get multiple values for the energies at different size cells.
My short comment on that is only that when you study things, the potential distribution at the molecular level near the electrode, a lot of complicated things related to packing, over screening, fluctuations, just due to water alone, not only to when you have a concentration, high concentration of ions. And in that way, just if we want to go further with that, using just a simple kind of a Poisson-Boltzmann approach, even with excluded volume, is not sufficient, because simulations show that the potential distribution is much more complicated. And you can influence by those, if you just don't consider those dipoles and consider your fluctuations of the electric field, static fluctuation related to the water structure, or ionic structure when it's very concentrated, it will be quite different. And so what the ion will feel, the dipole will try to be where you have a highest electric field locally. And it's quite just a complicated issue, but there is a lot of work in that direction.
Yeah, here we're making a very mean field static assumption. So not quantitative, and we're just hoping that the trends that we can get are correct. I would say that probably we can say what is big and what is small, but I don't think we could ever get a number. Like we could be like, oh, this step has to be rate limiting, or this step is facile and this step is difficult. But because of all the effects that you mentioned, all the dynamic effects that we're not accounting for, it's a qualitative.
Okay. Thank you very much.
Yeah.
So, thank you, Karen. I think, I don't know if there are other questions. Yeah, I find personally very, very stimulating your perspective and the relevance of the surface dipole as an effective pH producing an effective pH shift, and this explains the relation between surface charge and surface interface field and pH. It's very interesting.